Today's lesson is going to focus on our ionic and covalent molecules and the types of forces that exist within the molecule or between the molecules. These are called intramolecular or intermolecular forces. The difference between intra versus inter is stated within or between the molecules. So if you have an intramolecular force, this is within your molecule. So this is the actual bond that is occurring. And you either will have a covalent or an ionic bond. Your electrons will either share in a covalent bond or transfer in an ionic. When you have an intermolecular force, this is now talking about what is attracting two molecules to each other. So it's the attraction between two or more molecules, and this could be a dipole attraction, or there are two other types of attractions that can exist, which we will get to. Let's talk about ionic compounds first, the forces that occur for this type of compound. Ionic compounds, as we know, are repeating crystal lattices of ions. So because these ions repeat and repeat, they do not create molecules. And if they do not create molecules, they cannot have intermolecular forces. So they only contain intramolecular forces, which is the actual ionic bond, because of this crystal lattice that repeats. They are the strongest intramolecular force or strongest intramolecular bond because all of those ions have full positive and full negative charges that strongly attract each other. And as a result, if you try to melt an ionic compound or add heat to this structure, you're trying to break apart all of these attractions between positives and negatives, electrostatic attractions. And because those are the strongest attractions, you need lots of heat. And so they will have the highest boiling and highest melting points that exist. Water can come along. Water has a dipole, and water can attract these negative and positive ions of your crystal lattice, only if the ion attraction is not overly strong. So most ionics will dissolve in water, but if those ion charges are really strong, like +2 and -2 charges, or +3 or -3 charges, they will not be able to dissolve in water. Here's a nice visual of how a water molecule with its dipole, okay, here's the negative end and here's the positive end, can attract these ions. So here a cation, a positively charged ion, is attracted to all the negative ends of the water molecule. Here our anion, our negative ion, is attracted to all of the positive ends of the water molecule. When we talk about covalent compounds, they still have strong intramolecular bonds, so those sharing of electrons. But those sharing of electrons, we know, are weaker than ionic bonds. But because covalent molecules form molecules, they then have intermolecular forces, which again, ionics do not have. And they have three kinds. They have London dispersion forces, dipole-dipole attractions, and hydrogen bonding. And depending on the type of force that they have, or type of intermolecular force, will be dictated by whether your molecule is polar or non-polar. The type of intermolecular force will also predict their boiling points, melting points, and their solubility. The first intermolecular force we'll speak of is called London dispersion forces. And these forces occur in all covalent molecules. So regardless of whether the molecule is polar or non-polar. However, if the molecule is non-polar, it is the only intermolecular force. Okay, so London dispersion forces exist in all of them, but sometimes it's the only force if your molecule is non-polar. And when your molecule is nonpolar, you know you do not have an overall dipole in the molecule. So normally it looks like this, where the electrons are equally distributed throughout the molecule. But at any given point in time, those electrons will move around and they may clump up on one side of the molecule. When they clump up on one side of the molecule, they're negative. So they exhibit a negative charge. And on a neighboring molecule, you get this movement of electrons where the electrons will be repelled to the other side of the atom. And then this side that's empty is now slightly positive and can attract the negative end of a neighboring molecule or neighboring atom. This lasts for a split second. That is it. Okay, so they are very, very short-lived momentary dipoles. And because they are temporary, they are extremely weak and they form low boiling points, melting points, and very low solubility to water. They cannot dissolve in water. So if we look at nitrogen here and we just sort of move along to the different phases, to get nitrogen from a solid state to a liquid state and then to a gas state will take very little energy because, again, the attractions to break these weak, the energy needed to break these weak attractions is very low. And take a look, boiling point for nitrogen of negative, let's round, negative 200 degrees Celsius. This is extremely cold. We cannot comprehend how cold that is, but there's enough energy at that temperature to separate these molecules from each other. Molecules that are polar have a dipole. And if you have a dipole, those dipoles can be attracted between neighboring molecules. So because there is a constant polarization of charge, okay, if we come over here to our water molecule, there is a constant negative and positive end. Over here for our HCl molecule, oops, sorry, wrong way. Let's get rid of that. There we go. Chlorines are negative end, hydrogens are positive end. That dipole is always there. So as a result, those negative and positive ends can attract themselves, and we call this dipole-dipole attractions. These are medium strength attractions, and so therefore any molecules that can be attracted with a dipole have medium boiling points, medium melting points, and medium solubility to water. And this right here is a good visual of, again, the difference between intramolecular, that is the bond, right, that holds my molecule together. Intermolecular is the attraction between molecules. The last type of intermolecular force in a covalent molecule is called hydrogen bonding. And hydrogen bonding is just a stronger type of dipole-dipole attraction. So you have to have a polar molecule. You have to have a dipole on your molecule that exists. So just like in the previous slide. But the difference now is that you look for specific elements. So if you notice you have a hydrogen that is bonded to a nitrogen or an oxygen or a fluorine, who are the most electronegative atoms, that means you're going to have a real strong pull of electrons to one of those atoms. And that will just create a stronger polarization of charge. And then the negatives and the positives, when they're attracting each other, is just a stronger attraction than just a regular old dipole attraction. So we call that specifically a hydrogen bond. And these are the strongest types of dipole attraction, which means they will have the strongest boiling points, melting points, and solubility to water. So how can you predict which type of intermolecular force will be present in a covalent molecule? So remember, IMF's intermolecular forces are not present in ionics. So the only way to do this is to draw them and then determine the polarity of your molecule. So if we look at hydrogen, we know that the difference in electronegativity is 0, which means we have a nonpolar bond. If this is a nonpolar bond, this is a nonpolar molecule, and the only attraction you'll have in there are London dispersion forces. That's all that can exist. If we look at carbon dioxide, the difference in En between carbon and oxygen is 0.89. This is a polar bond. And if it's a polar bond, we're going to have electrons being moved to our oxygens, but it's an equal pull. So overall, this is also a nonpolar molecule. And if this is a nonpolar molecule, that means that the only forces of attraction I have are London dispersion forces. Here's ammonia, and ammonia's difference in electronegativity is 0.84. So if it's 0.84, we know that that's a polar bond. And when we look at our molecule, we see we have poles going towards the nitrogen, but not in all directions. This makes my molecule polar. And so I know I'm going to have dipole-dipole attractions, but I also notice I have nitrogen bonded to a hydrogen. So I'm also going to have H bonding happening here. And here's water. Everybody should know by now that water is polar. Okay, it has a dipole through it. This is what makes it so unique. And then I notice again, I have a hydrogen and an oxygen bonded together. So I am going to have H bonding present.